So today we are going to define linear operations, which are these two operations on vectors. This one is the addition of two vectors and this one is the scalar multiplication, where you multiply a vector by a scalar. Now before we see the actual definitions though, there is a small discussion that the author has. So let's see what he has to say here. And this is important. Since vectors are abstract quantities, they are mathematical quantities. We can define sums and products involving them in any way we like. That is just like saying that you have the game of chess, right? So when the game was developed, some people had to come up with the rules for how the chess pieces move, right? For the first time, someone decided that rooks would move like this or like this. Bishops would move diagonally. Knights would move in a complicated way. So they could have given different rules also, creating possibly a different game. So just like that, we can, because these are abstract quantities, mathematical quantities, so the rules for addition and multiplication or whatever else we ultimately define which involve vectors, they can be anything actually. We can do just about anything, we can define these operations in any way we like. However, we should not forget that we are not just playing with vectors. We are doing these things and there is a purpose. Do not forget that the source of mathematical vectors, these abstract quantities, are our physical vector quantities. Velocity, acceleration, momentum, force, all these things which arise in reality. So we actually abstracted the idea of vectors from those vector quantities which are physical quantities, and that is why then the author says, but in order to be of any use, the definitions must create a coherent algebra. This, however, is mathematical, this part, and represent something of interest when applied to a range of vector quantities. They should ultimately end up being useful when you apply them back to those physical quantities. That is why we cannot just simply define these operations in any way we like. Although we can, but that won't really be of any use. That will ultimately just simply be a mathematical game. And there is something else also. Also, our definitions should be independent of the particular representations used to construct them. This last part will better be understood when we see the definitions. And these requirements are satisfied by the definitions that ultimately were chosen as the definitions of vector addition and scalar multiplication. I mean, people who worked with these things, they did this carefully. So here is the definition of the vector sum a plus b. Let a and b be any two vectors. So these are abstract vectors. Let pq be any representation of a. You look at this word any carefully. Okay, any representation of the abstract vector a. And you also recall at this stage that we have decided to use directed line segments, which are geometric quantities, as our models for abstract vectors. That is why this is a line segment which is having some length and it is directed from P to Q, and it represents the abstract vector A in the sense that the magnitude of A equals the length of the line segment PQ, and the direction is the direction of PQ from P to Q. And let QR be a representation of B. This time we are not writing any representation. Okay, we will come to these things. Why this is any, why this is A. Then the sum A plus B of these two vectors is that vector which is represented by the directed line segment PR, where P is the initial point of this representation of A and R is the terminal point of this representation of B. Alright, now let us try to understand what's going on here. So you have an abstract vector, it may be any vector, and it is represented by the directed line segment PQ. Why did the author use the word any here? That is because a given vector has infinitely many different representations. You can see the figure here. I have used this directed line segment as a geometric representation of the abstract vector A. Now instead of precisely this O, see this is nice, no? I mean it is actually matching the length of this, I did not do it consciously, it just happened, of this marker. So instead of using this exact directed line segment precisely in this location, in this universe, you can instead use this directed line segment also as a representation of your A. This one, not that one. And you can, because same length and same direction. Alright. And then we are saying that let QR, so this is your new position of, it's not exactly Q, it is some other point, but say you are, so we have understood why we can write any here, alright, and this is our Q. Now next we are saying let QR be a representation of B. The question is this, how do you know that there will exist a representation of B which starts with Q, given that this Q is just some point and this Q actually depends on your choice of PQ, right? Instead of choosing precisely this PQ, you can choose this PQ or this PQ, this one. So many, infinitely many different choices are there, and you are in fact emphasizing that by writing any. But then how do we know that starting from that terminal point of this representation for A, we will have a representation for B, and the terminal point will be the initial point of the representation for B. That is because whatever B is, no, I mean whatever its magnitude is, whatever its direction is, that can start from any point. In particular, that can start from this Q, or if you are using this PQ, from this Q. Instead of this, you can use this. See? Same thing. Same direction, of course, you have to maintain the same length. And then how do you define sum? You then define the sum to be that vector, some abstract vector, which has PR as its representation. Instead of this PQ, if you use this PQ, and instead of this QR, this one, then this will be the sum. I should not perhaps say this sum, but a geometric representation of the sum, and this one represent the same abstract vector because same magnitude and same direction. So now do you see that previous remark that our definitions should not depend on the particular representation that we choose to create them. So that is being satisfied here, and this is the vector sum. It's a bit strange that this has been chosen as the definition of sum, but as was discussed just now, that people who work with these things, they carefully saw what they want out of this abstract thing, so that when they apply this back to the actual vector quantities, there they get something meaningful. That is why the definition is like this. So now everything is clear about this definition. Again I am saying this PR itself is not the vector A plus B. It is a geometric representation of some abstract vector which we are calling the sum of A and B. There are infinitely many such representations. So that's the sum of two vectors. Now next we have two laws of algebra for vector sums. There are a few others also, but these two are, they come first. vector addition, the operation that you saw just now, is commutative. This means that it does not matter in what order you take the vectors when forming the sum, the result is same. A plus b is equal to b plus a. And a proof of this law, you can do it yourself using just the definition, or you can find it in any book on vector algebra. Actually, this part we are not really going to see all the proofs in this part. It's in the vector calculus part that we are going to be really very thorough and prove everything. And this is the next one, which you can express by saying that vector addition is associative. This means that if you have three vectors and you form their sum, obviously the operation itself does not involve three vectors, it involves two vectors. That is why you need to mention the order in which you are going to perform the sum. This one which you see on the left hand side of this equation is actually the sum of two vectors. One of them itself is a sum of two vectors, a plus b, and the other one is c. This one, however, is the sum of a and b plus c. This law says that they are actually the same. And proving this also using our what is this called, geometric model of directed line segments, is an extremely easy thing. You can do it yourself. So we are next going to see the next operation, that is multiplication of a vector by a scalar. But before we see that, let me just show you one more thing, which actually, we cannot call it a proof, but let us actually see that if you add the 0 vector to any vector, you get that vector, that any vector, as the result of the sum. A proof of that fact, which is just merely an observation. So you see this equation. This is what we expect to happen, but does it really happen with this definition of addition, that when you add the 0 vector to any vector, you get that vector back? Let's see. Say PQ is a representation of the abstract vector A. But then you saw the definition of addition just now. What do you do for the other vector? You think of QR. That R, where it will be located, that depends on what that other vector is. Because that other vector in this case is the 0 vector, which is represented geometrically by a point. Or you can actually think of it as a line segment having 0 length, but there is no direction because of this lack of length. So that R in this case is Q itself. And what does the definition say? The definition says that then the directed line segment PR represents the sum geometrically. In this case, because Q itself is R, so the sum should be that vector whose geometric representation is PQ, but that is just A. That's why. Actually, before we define scalar multiplication, we have to define the negative of a vector. I forgot, in fact. You can in fact define scalar multiplication first, and then you can define the negative of a vector as a special case, but here the author has chosen to define it first. Because this does not have a heading, so here he has written negative of a vector. Let B be a non-zero vector. In the text, this definition itself is there, but I have made a slight change. It is not given in the text that let B be a non-zero vector. It's just simply given that B is a vector. Let us first see what the definition is. Let B be a non-zero vector. That vector which has the same magnitude as B but opposite direction is called the negative of B. And we denote it by writing minus B. The arrow overhead will always be there if it's a vector. And we are going to, because this is non-zero, we are going to separately define the negative of the 0 vector. We define the negative of the 0 vector to be itself. That's it. And we also, just like this one, denote the negative of the 0 vector by writing minus 0. That is, minus 0 is defined to be equal to 0. I am going to use this symbol, that is colon followed by the equality symbol, to define something. In what sense? In this sense, the quantity or whatever you will have on the side of the colon, that is the object, idea, anything that is being defined, and the meaning will lie on this side. Okay, this is something whose meaning is this. That's what this symbol means. Okay, we are going to use this when defining something. For example, if you define an ordinary function, you would write f of x here and the formula on this side, like that, in that sense. In the book, the author simply just defined the negative of a vector, any vector. But the problem is that you cannot talk about the direction of the 0 vector. If your b is 0, there is no direction. Then what does this mean? That is why. Now, once you have addition and negation, that is the operation of negating a vector is called negation. You can define subtraction simply like this. If a and b are any two vectors, we define subtraction with this equation. Here also again you see I am using this colon followed by equality. This means that this is something new that I am defining, and its meaning is this. A minus b means the sum of a and the negative of b. Now let us also see what you get if you use geometric representations of this vector. I mean, just we draw a diagram like the one we drew when defining sum. So you look at this diagram. A is some vector and b is also some vector. Say this is a geometric representation of A, this directed line segment, and say this is one for B. So then a geometric representation for minus b will be what? Minus b by definition is a vector which has the same magnitude as b. And the fact that this is a geometric representation for b tells us that that magnitude is represented by this length. So, to represent minus b, you have to choose a directed line segment whose length is the same as this one, same, and the direction should be opposite to what that one had. Alright, so that means this is a geometric representation for minus b, and we have chosen this one because its initial point coincides with the terminal point of A, which we need in order to think of the sum of A and minus b, which by the definition of sum is this. Actually, it is not exactly that, but it is that vector whose geometric representation is this, and any other directed line segment which has the same length and same direction would also represent this A minus b. And now we can define general scalar multiplication. So this is the definition of the scalar multiple lambda A, definition 1.5. Let A be a vector, any vector, okay, it may be 0 also, and lambda be a scalar, which means that lambda is a real number. Then the scalar multiple lambda A is that vector, that abstract vector whose magnitude is this. Let's look at this magnitude carefully. What do you see here? Modulus of lambda times, we seem to also have modulus of A, but of course there is a difference between this one and this one. This is the absolute value of the real number lambda, which is what? If lambda is a non-negative real number, then this is just lambda. Otherwise, if lambda is negative, then this is equal to minus lambda. This, on the other hand, is the magnitude of the vector A. Alright. So this is the magnitude of this lambda A, that abstract vector. But what about its direction? And now we are coming to that, and whose direction is given by these three conditions. The direction of this new vector is considered to be the same as A if the scalar by which we are multiplying is a positive real number, if lambda is greater than 0, and the direction of this is undefined. There is no direction if lambda is equal to 0, and actually the meaning of this second condition is just that if lambda is 0, then we are defining lambda times A to be the 0 vector, and that is why there is no direction. But does that match with this, this definition of magnitude? Yes, because if A is 0 or non-zero, that we don't know. If lambda is 0, then its absolute value is 0. So this real number is 0. Okay, do you see that? This is actually a real number, and that is 0. So that is why in this second case we get the 0 vector. And if lambda is negative, then the direction of this vector is considered to be the same as minus A, or you can just simply say it's in the opposite direction as A. That is, it has that direction which is opposite to whatever direction A has. It is just for this maybe that the author defined the negative of a vector before this, but you can define it first and then define the negative using this. So this is your scalar multiple. Now it's an easy consequence of this definition that you have this minus of lambda times A is equal to minus lambda times A. You can prove it yourself by going through these three cases separately. You can see it for yourself, or you can just assume it as something given. You must have already gone through these identities and proved all of them before in your some course on vector algebra. Do not forget that our main aim here is not studying these mathematical things. We want to get into mechanics. Next, we also have these laws of algebra involving scalar multiplication. You have this one law which tells you that lambda times mu A equals lambda mu times A, and you of course understand that here lambda and mu are real numbers. You can call it a kind of associative law, and you also have these distributive laws. The scalar lambda times the sum of the two vectors A and B equals lambda A plus lambda B, and this other one which has two scalars and one vector. Lambda and mu are scalars and A is the vector. Lambda plus mu times A equals lambda A plus mu A. Actually, if you collect all these properties plus one or two others which we did not see here, then all those things collectively say that the vectors we have, they form a vector space over the field of real numbers under the two operations that we see here, vector addition and scalar multiplication. What this means, we do not have to bother about that, but I said it now because you remember that in the beginning the author discussed a little, and there he mentioned that the operations should lead to a coherent algebra, and that algebra is this fact that this entire system is a vector space. And let's not worry about what vector space means or those things. We may need what vector space means, we may need the meaning afterwards, but we will see it then. Now, in order to see that we have really understood these operations and the properties that they have, we have this example which asks us to simplify this expression involving two vectors A and B, some vectors, and these real numbers 3, 2, you can see them. So we have to apply whatever rules we saw here and simplify this expression. Turn it into a form which is simpler than this, and we won't do it carelessly. At every step we are going to see exactly what we have used. So we first take this expression, we write it here. Okay, we write it as a solution, we have this. And then we write what these things really mean. What is 2a minus 4b? 2a minus 4b is the sum of the two vectors 2a and minus 4b. And there also there is a little something. Minus 4b is the negative of the vector 4b. So I have used brackets here as well. Just like that, here we have minus 2 times 2a minus b, which is the sum of 2a and minus b. Actually I should have used another set of brackets, but you do understand. Okay. But then what do we do? In place of minus of 4b, we are writing minus 1 times 4b. What is this? This comes from that thing which we wrote there. Minus lambda times a is equal to minus of lambda times a. Or I should have said it like this: minus of lambda a is equal to minus lambda times a. And there, if you take, in place of lambda, if you take the real number 1, then you get minus of a equals minus 1 times a. That's the thing we have used to write this in place of this and this in place of this. Alright, now, so then in the next line we do multiplication. We multiply this sum by 3. But what allows us to do so? Namely that law which tells us that lambda times a, this of course is 2a, I am talking about the general law. Lambda times a plus b equals lambda a plus lambda b. You do not exactly see this b here, I did something else simultaneously. In place of writing minus 1 times 4b, I have written minus 1 times 4 times b. And what did we use here? Namely that law which tells us that lambda times mu a is equal to lambda mu times a, that thing. And then we multiplied this one also similarly by minus 2, obtaining minus 2 times 2a plus minus 2 times minus 1b. And then whatever we did here from this to this, to get this from this, we do that same thing to all the terms in the next line. 3 times 2a is 3 times 2 times a. 3 times this will be minus 4, so you have 3 times minus 4b. Here minus 2 times 2a minus 2 times minus 1b. And then you do the calculation. This will be 6, this will be minus 12, this is minus 4, and this last one is 2. Okay, so that's how it has come to a form which is much simpler than what we started with, but still you can do more simplification. So in the next line what we do, in place of 6a plus minus 4 times a, we write 6 minus 4 times a. Obviously it looks like something that we should be able to do, and we can do, but using which rule, which property? It is that property which tells us that lambda plus mu, you do not see plus here, but think of it as 6 plus minus 4. Lambda plus mu times a equals lambda a plus mu a, lambda a plus mu a. Okay, using that. So that way you are getting 2a here, and similarly minus 12b and plus 2b give you minus 10b. And finally, instead of stopping here itself, you can write this like this. I leave it to you to exactly understand why we can write this in place of this. By now you must have realized that it's not just that we do not want to use brackets, it's our laziness. This means one thing and this means something else, but actually they are equal. And there is one more subtle point. We do not have that here. I mean, we got these first two terms in this entire sum by multiplying by 3 another sum, right? So ideally we should have used brackets here, and then these two terms we got from that next one, minus 2 times this plus this plus this. So here also we should have used brackets, but we did not use brackets. Is that okay? Yes, that is okay, because of the fact that vector addition is associative. If you add to a plus b another vector c, you get one vector, and instead of that, if you add a to b plus c, you get that same vector. So in a sum involving a finite number of vectors, it does not matter how you do the calculation, which vectors you add first. That is one thing. And the other thing is that which you may have missed here, is that the order in which the vectors are written also does not matter, because vector addition is commutative. These two things, that vector addition is associative and vector addition is commutative, allow you to rearrange the vectors in a sum which has finitely many vectors. And actually we did that here to get from this step to this step. You see that we have written 6a minus 4a as it's as if we have first taken them together and then we applied that law. And actually that's the thing you should do, because you only have lambda plus mu a when you have lambda a plus mu a together. They are not together. How to get them together? By changing the order of this vector and this vector, which you can do because vector addition is commutative. That is why. And when you change that order, minus 12b also comes with 2b, and that is why here also you can use that rule. And that's how you see that whatever we normally do carelessly has all these things behind such calculations. But do not be afraid. We are perhaps being so boringly detailed with everything for the last time. And that's just it. After this we have, we of course have many things. We have the notion of unit vectors, then a basis of vectors, a basis set. These are the things that we will see in the next mechanics video.